Well, hello, friends. We've done it. We've made it to Unit 7, Lesson 4, Part 2, Derivatives of Logs and Absolute Values. And if we were in a normal school setting, this would have concluded everything we need to know about differentiation. All right, so here we go. Let's tackle it head on. When we are using the power rule, do we ever have a function whose derivative is x to the negative 1? So for instance, like if I asked you what is the derivative of x squared, you would tell me that the derivative of x squared by power rule is 2x to the first. If I give you the derivative of x, it's technically 1x to the 0, but x to the 0 is 1, so it's just 1. And that's the problem. In order to get this negative 1, even if I have x to the 0, I would take 0 times x to the negative 1. Well, that's just 0. So let's determine if such a function does exist. And how is that function going to exist? We're going to do the proof of the derivative of the natural log of x. So here's what we're trying to prove. We are trying to prove that y, what is the derivative of y equals the natural log of x? All right, friends, here is the issue. I don't have a derivative rule for the natural log. That's what I am trying to figure out. Let me make this so bold. So what are we going to do? Friends, we are going to exponentiate this. What do I mean by that? Doesn't this mean y equals the log base e of x? And don't we rewrite this not in log form, but when we exponentiate and we put this in exponential form, don't I have base e? A log is an exponent to the power of y equals my argument, which is an x. So these two statements are exactly the same. Well, why do we want to do this? Because now I can differentiate both sides. Now, the right side is easy. The derivative of x with respect to x is just 1. But friends, implicit differentiation kicks in. So what is the derivative of e to the y? Well, it is just itself e to the y, but then I have to multiply it by the derivative of y with respect to x. And then when I solve for dy dx, I end up with 1 over e to the y. Well, that's not very useful, but let's recall. Don't we know from this purple step? So this purple step right here, didn't we say that e to the y is equal to x? What is a lot more useful is if I substitute x in for e to the y. So friends, the derivative of the natural log of x is 1 over x, aka x to the negative first. So going back to our original question, when we are using the power rule, a polynomial doesn't yield a derivative of x equals negative 1, but a natural log of x does. All right, so your formal rule is written in terms of chain. So the derivative of the natural log of u is 1 over u prime. So just to kind of get you like thinking, this is how I always remember my derivative rules. We have exponentials and we have logs. So when I wanted to take the derivative of e to the u, it's just itself times u prime. Well, when I want to take the derivative of the natural log of x, let's do that in terms of u. The natural log of u, it's 1 over u times u prime. And sometimes you'll see text write it as u prime over u. Okay, we'll fill out like this part a little bit later in the lesson. So how do I do my homework? Most of these are pretty straightforward. Again, if you want to think of this in the bigger picture, we have limit definition, which we don't really want to use. We have our basic derivative rules. We have product quotient. We have chain. We have implicit differentiation, which we do when it's not in terms of y equals. We learned about derivatives of, and then related rates was application thereof. Then we learned about exponentials, where we had base e and non-base e. We're currently learning about logs. We're doing the natural log right now. And then don't forget that you have this in addition to your trig and your inverse trig derivatives. So when I'm looking at a problem like example 1, I'm saying to myself, You know, which one of these rules kicks in? And hello, this is a natural log. So the natural log tells us to take 1 over 2x times the derivative of 2x, which is 2. And when we simplify, we end up with 2 over 2x, which gives us a final answer of 1 over x. So notice that coefficient of 2 really did not affect our final derivative. Okay, let's do the derivative of natural log of x squared plus 1. Again, in the big picture, you need to think about, well, which one of these applies? Do we use basic? And to some extent, we will when we find the derivative of the inside. We'll use sum and difference rule and power rule. But we're going to have to apply chain rule. We have a log rule. So again, they all work in terms of gears. So the main idea is this is a natural log. So the derivative of any natural log is I take the reciprocal of the argument times the derivative of the argument, which yields me a final derivative of 2x over x squared plus 1. Example 3, why did I give you this? Because when you look at this again, you have to remember this big pot. This is everything you know. What kicks in? Well, in this problem, you have x times the natural log of x. Therefore, product rule is going to kick in. So my f function is x, which yields an f prime of 1. I have a mistake, hold on, of 1. And then g is the natural log of x, and g prime is 1 over x. So when we do f prime g, I get the natural log of x plus x times g prime, which is going to yield a final answer of the natural log of x plus 1. So for example 4, we're taking the derivative of the natural log of x to the third. So you have to think of this as this is actually a problem that we're going to begin with our basic rules and with a combination of chain. You can think of this as u to the third. So when I differentiate u to the third, it's 3u to the second times u prime. It's just our prime in this case is going to be a log derivative. So I'm going to start my derivative by taking 3 times the natural log of x squared. That's just plain old power rule. But now I have to multiply by the derivative of the natural log of x, which is 1 over x. So this yields a final answer of 3 natural log of x squared all over x. Okay. So why did I pick this problem? I picked this problem because we do not like that square root, friends. So let's do an algebra rewrite step where I write this as the natural log of x plus 1 to the 1/2. Now, you have some choices. You absolutely have some choices. You can basically start differentiating by making this 1 over x plus 1 to the 1/2 and multiplying it by the derivative of x plus 1 to the 1/2. So by chain rule, you would have 1/2 x plus 1 to the negative 1/2, technically times 1, which yields a final answer of 1 over, that 2's on bottom. This term would be on bottom, and when you add, what the heck did that do? Let's erase that. This should be a 2. All right. When this term right here goes downstairs, there's already an x plus 1 to the 1/2 term, so you get x plus 1 to the first. That is one way you can go about doing this problem. An alternative way that you can go about doing this problem is to apply a property of log first. So I'm going to do another algebra rewrite step, and I'm going to write this as 1/2 the natural log of x plus 1 because you have the power to a power rule which tells you to multiply the exponents. So remember, a log is an exponent. It's being raised to an exponent. So I am taking this exponent and that exponent and multiplying. When I differentiate, I can bring the 1/2 out by constant multiple rule. And then f prime of x is equal to 1/2 times 1 over x plus 1. And I get the exact same answer I did before. And in one woman's personal opinion, I feel like doing this algebra step was pretty life-changing. Come on. I don't know. I just felt that it was a lot easier than dealing with chain rule with the negative exponent. But again, that's my opinion. All right, number 6. I can tell you right now, I will know if you bothered to watch this video. I will know if you bothered to look at your filled in notes, because if you are a student, do not put your pen down right now. Do not write this. If you're a student that starts this derivative by writing 1 over this, and then you're going to take the derivative of this, I'm just not going to grade it. This is not efficient. This is not how you go about at all. This is not how you go about differentiating this at all. That is a waste of your time. That is not good calculus. Even if it's valid, it's just not good calculus. What should you do in this case? So I will know it. Look at the WPE. There's a couple of questions on there that I will be looking for you to use your properties of of logarithms. You need to apply your properties of logs before you start differentiation. So what do I mean by that? Well, I'm taking an algebra step. I have a quotient. So this tells me to take the natural log of x times x squared plus 1 squared. And I need to make this a little bit smaller. All right, and we're going to subtract off the natural log, and I'm going to go ahead and write that as 2x cubed minus 1 to the 1/2. All right, let's do another algebra step. We're not done. Last year in Algebra 2, you would have done these on the condense problems. We're currently expanding. So that's why you needed to practice this last year in Algebra 2 trig. All right, so now I have x, and I have x squared plus 1 squared. That's a product. So that means I'm going to take the natural log of x, and I'm going to add it to the natural log of x squared plus 1 squared. And I'm just going to rewrite this. All right, next, let me make this a hair thinner. All right, next, for my last algebra rewrite step, I'm still in algebra. All right, the natural log of x is cool, but I have this square. Again, it's a property of logarithm. I can bring that in front. And then I'm going to do it on here as well. Now I'm going to do my calculus step. And my calculus step will look like f prime of x. So you are really using your sum and difference rule, because I have 3 separate terms, and I'm going to take each of their derivatives and then add them together. So the natural log of x is 1 over x. Life is good. Then next, 2 by constant multiple rule, and you're going to have 2 times 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus the 1/2 can just stay out by constant multiple rule. 1 over 2x cubed minus 1 times its derivative, which is 6x squared. So for a final answer, you do not need to make a common denominator. Oops. I have 1 over x for the first term. I have 4x over x squared plus 1 for the second term. And then for my last term, let's see, the 2 and the 6 cancel. So I'm left with a minus 3x squared over 2x cubed minus 1. Because the natural logarithm is defined for negative numbers, you will often encounter expressions of the form the natural log of u, of the absolute value of u, excuse me. Basically what this is saying is if you are presented with this, you can just treat it like the natural log of u. Why? Here is the proof for that if you're interested. If u is greater than 0, then you're basically saying the absolute value of u is always coming out as a positive. So it just holds true that the derivative of the natural log of u would just be 1 over u times u prime. However, what would happen if u was less than 0? Then you would be asked to take the derivative of the natural log of a negative u, which when you differentiate would give you 1 over negative u, but when you multiply by chain, you would get a negative u prime, and then the negative times the negative in turn makes a positive. So you still end up with u prime over u. So the bottom line is that if you're ever presented with a problem where you're asked to differentiate the natural log and they put that in an absolute value, you really can just treat it like the natural log and drop the absolute value. So what does that mean here? Find the derivative of f of x is equal to the natural log of the cosine in x. You really can just treat this as the natural log of cosine of x without the absolute value bar. That's what we just went through. So this derivative would be 1 over the cosine x times the derivative of cosine x, which is negative sine x. And full credit for NAP would be negative sine x over cosine x, but they would probably write this as a negative tan x. What if we need to differentiate a logarithmic function for a base other than e? So again, see if I'm going to keep writing this grid throughout this lesson so that you can kind of compartmentalize. So again, we'll put exponentials in the top two quadrants. We'll put logarithmic in the bottom. So when we differentiated e to the u, it was itself times u prime. When we differentiated the natural log of u, it was a format or a structure that was the reciprocal times u prime. When we differentiated an exponential, let me make that a u, I'm sorry, an exponential that is other than base e, remember it was itself times u prime, but remember how we had to multiply by the natural log of that base? We had this extra factor. Okay, I want you to remember that because what we're about to do right now is we're going to talk about what happens if you have to differentiate a log of a of u other than the natural log, and you're going to see a similar pattern. So when we do the proof of the derivative of log base a of x, again, we're trying to differentiate log base a of x, and I don't have a log rule. Rewrite this in terms of a function that we know how to differentiate. So I'm going to refer back to our properties of logarithms. And we had a property of logarithm. It was called the change of base. All right, so it was from that handout. And on the change of base, if you've got something that is log 4 of 12, I could write it. Well, I didn't want to undo. I wanted to circle. You can rewrite it as the natural log of the argument over the natural log of the base. Why would we want to do that? We want to do that so that if I rewrite this as y equals the natural log of x over the natural log of a using change of base, this is now in a format where we do have a derivative rule because I can find the derivatives of natural logs. I furthermore want you to think of it like this. The natural log of a, that is a constant. So I want you to think of this as 1 over the natural log of a, that's a constant, times the natural log of x. Why would I want you to do that? Because y prime is going to equal 1 over the natural log of a by constant multiple rule times 1 over x. So the derivative rule for log base a of x is 1 over x. It's very similar to the natural log, but then it includes that natural log of a. So if we go back to this grid that I showed you, what we just determined is if I want to take the derivative of a log that is not the natural log, okay, I still do 1 over u like I did for a log rule. That's the structure. And I would still have to multiply by u prime, but then I have to include that natural log of a, which was the same thing when you had to differentiate an exponential that was not a base e. So hopefully you can draw those parallels. So here is your formal definition. If you're trying to take the derivative of a log and it is not base e, then you take 1 over the argument. You have to include that natural log of a and apply chain rule when appropriate. So how do I find the derivative if it's log cosine of x? Because there is nothing written here, this implies that it is the common log. So y prime is going to be 1 over the cosine of x. The derivative of the cosine of x is negative sine x. And furthermore, you have to multiply it by the natural log of 10 because a common log is 10. So I would have full credit if it was negative sine x over cosine x natural log of 10. I don't know why I just wrote x. Or Bob's answer would probably give you a negative tan x over the natural log of 10. All right, example 9. All right, how do we go about doing this guy? Use properties of logs first. If I see you, don't write this down. If I see you doing 1 over x, the square root of x minus 1 over 2, then you have to differentiate it. Then you're going to multiply it by log 3 in the denominator. I'm not going to grade it. That is not, even if it's valid, that is not an efficient way to differentiate logarithms. So what am I going to do first? I'm going to do an algebra step. All right, this is going to be log base 3 of x square root of x minus 1 minus log base 3 of 2. This is awesome. That's a constant. When I go to differentiate that, it's just going to be 0. I'm going to take one more algebra step, and please note that if you can expand in one step, please do so. I'm just doing it in steps for friends who might not be as strong in logs as they want to be. All right, so I've log base 3 of x, and since this is a product, I'm going to add log base 3 of x minus 1 to the 1/2. I'm going to get that out of there, and it's still minus log base 3 of 2. And then my final expand step is f of x is equal to log base 3 of x plus 1/2 log base 3 of x minus 1 minus log base 3 of 2. So now I am ready to proceed with my calculus step. F prime of x is going to be, this is the derivative of a log that is not base e, so it's still 1 over x, but I have to include the natural log of 3. In the second term, I'm going to pull the 1/2 out by constant multiple rule, and then it's going to be 1 over x minus 1, but then you have to multiply by the natural log of 3. And this right here is a constant, so it's technically plus 0. There's really no way to write this all nice and neatly. I would just leave it as 1 over x natural log of 3 plus 1 over 2 natural log of 3 times x minus 1. All right, in the next problem, I gave you this because when you look at its structure, this is a product. So we're going to have to use product rule in order to differentiate. So if f is going to be x to the 3/2, that means f prime is going to be 3/2 x to the 1/2. If g is log base 2 of x plus 1 to the 1/2, I can think of that as 1/2 log base 2 of x plus 1. So g prime, I'm still going to keep the 1/2. And it's going to be 1 over x plus 1, but then I'm going to have to include the natural log of 2. So when I do f prime g, I'm going to get a hot mess. So I'm going to get 3/2 x to the 1/2 times 1/2 log base 2 of x plus 1. And then I'm going to have to add f prime, which is x to the 3/2, all over 2 times the natural log of 2 times x plus 1. And you guys, there's really no good way to clean this up. I would just write this as a final answer of, this is going to be 3x to the 1/2 times log base 2 of x plus 1 all on the top, all over 4. And then I just have that x to the 3/2 all over 2 times the natural log of 2 times x plus 1. Okay, so sometimes the properties of logarithms can be used to simplify the differentiation process, even if we must introduce the logarithms ourselves as the step in this process. So the last part of this video is about teaching you a process called logarithmic differentiation. So if I want to talk about derivative formulas, we have derivative formulas for our basic differentiation rules, for product, for quotient, for chain. We also have them for trig, for inverse trig, and we just finished learning about exponentials and logarithmic. But if we want to talk about a process, I taught you a process that is implicit differentiation. It's not a formula, it's like a how-to depending on how you are presented. I'm going to put logarithmic in this category. It is analogous or parallel to implicit in that it is process oriented. It is not formula driven. So what do I mean by that? Classic problem. Classic problem where kids go, what the function, Nop? How do I differentiate this? You guys, you can't use basic rules. Why? Because when you use power rule, it is based on the premise where x is your unknown and n is some rational number. Well, this is x to the x, so that is not a rational number. I also cannot apply an a to the x, because if this is an exponential that is non-base e, this implies that your base is a constant. And in this case, it's not. So when I listed all of those ways that we differentiate, all those ways, all right, you guys, none of these apply in terms of formula. Basic doesn't apply. None of these apply. What is going to imply is logarithmic. Why? Because if I have y equals x to the x, I'm allowed to take a log of both sides. Now, don't write this down, but if you want to get wild and crazy, you are welcome to take log base 43 of both sides. You can. It's still going to work. But why am I not going to do that? Because if you choose to take an log with a base other than e of both sides, well, then you're going to have this extra natural log of whatever base you pick, this extra factor all over your work. I can avoid that if I decide to just take the natural log of both sides. So this gives me the natural log of y is equal to natural log of x to the x. Now I can apply algebra rules by my properties of logs. And now I'm actually going to use implicit differentiation. And now I am going to use my log rules to proceed. So now is my calculus step. So let's get a new color. And this is my calculus step. The derivative of the natural log of y is going to be 1 over y times dy dx. And then, friends, I'm going to have to use product rule. So my f is x, my f prime is 1. G is the natural log of x, and this is why I picked the natural log, not log base 4, not log base 10, because the natural log of x is 1 over x, and I don't have that extra natural log factor in my work. So when I do f prime g, I get the natural log of x. And when I do fg prime, I get x over x. So I get dy dx is equal to the natural log of x plus 1 times y, because I multiplied by y on both sides so that I could solve for dy dx. And again, I don't know that I have a huge problem with that, but this is in terms of x and y. For your final answer, didn't we have a statement that y is equal to x to the x? So if I want your final answer in terms of x, and if we were in class and we had a test, I would tell you I want an explicit answer. Dy dx is equal to x to the x times the natural log of x plus 1. So again, I would call this the explicit form of the derivative, and we would have called this the implicit form of the derivative. Okay, and here is our last example. What I wanted to show you is while this is explicit form, And it is absolutely mathematically valid to do quotient rule or to rewrite the bottom and then use product rule, and you are welcome to do that. You can use logarithmic differentiation anytime you have a really complicated function. So why would I do this? Well, here's why. I'm going to take a natural log of both sides. This is an algebra step, not a calculus step. Why would I do that? Because if I take a natural log of both sides, and again, I'm choosing natural log instead of a log other than base e, because when you differentiate a log of other than base e, this is going to cause me to have a natural log of a factor somewhere in my work. Doing this allows me to apply properties of logarithms. So this is going to give me the natural log of y is equal to the natural log of x minus 2 squared minus the natural log of x squared plus 1 to the 1/2. In a further algebra step, this gives me the natural log of 2 natural log of x minus 2 minus 1/2 natural log of x squared plus 1. And again, why on earth would I want to do that? Because now when I do my calculus step, I'm just going to get 1 over y times y prime equals 2 by constant multiple rule over x minus 2, technically times 1, the derivative of that is 1, minus 1/2 by constant multiple rule over x squared plus 1 times the derivative of the interior, which is 2x. And friends, for some of you, this is a better alternative than having to do quotient rule, because now I'm done with my calculus. The rest of this is just going to be simplification. I have 1 over y times y prime is equal to 2 over x minus 2. And if I simplify, I get minus x over x squared plus 1. And if I'm not going to get into too much algebra due to like e-learning, but if I wanted just the implicit form of this derivative, it is just y times 2 over x minus 2 minus x over x squared plus 1. If you wanted the explicit form, well, then you need to put the original function back in for y. So the explicit part would be x minus 2 squared over the square root of x squared plus 1 times 2 over x minus 2 minus x over x squared plus 1. Sorry, I ran out of room. And if you look in the filled in notes, it has more simplification. I'm not requiring it at this point in the semester. I can't even spell, guys. That's the kind of day it's been. Simplification, if you look at the filled in notes, but ultimately I'm good. All right, the last thing that I want to let you know is there is a derivative rule. So this is a picture from the beginning of your textbook. So just to be clear, you don't have to do any of the problems that you see that are hyperbolic, but we have covered all of these rules. Number 1 is constant multiple rule, sum and difference, product rule, quotient rule, constant rule, power rule, identity rule. This is the one we didn't cover. It's pretty straightforward. If you want to differentiate an absolute value, it's the stuff inside the absolute value over the absolute value, and then you use chain rule. So I know that didn't really come up much, but just add that to your repertoire. We just finished the natural log. Here is exponential base e. Here is log other than base e. Here's exponential other than base e. These are all of your trig derivatives, and here are all of your inverse trig derivatives. So congratulations, you should be able to differentiate anything. So for this week, all right, this right here is your recommended assignment. This is the if you are bored assignment. And on April 24th, WPE number 7 is due. See me if you need to at office hours at 11:30 on Tuesdays and Thursdays. Bye, friends.